module looks at salts from mantle-derived processes. They're not true evaporites, they're not solar powered, they're not related to uptake of solar heat by a brine on or near the Earth's surface. Rather, they're related to a variety of retrograde salts and also the supercritical properties of brines at extremely high temperatures and pressures in the subsurface. There are many other situations where ionic salts or saline minerals can form that are in regions where we do not see brine concentration driven by solar evaporation. So these are not true evaporites. Their mother brines typically come from a variety of magmatic, brine mixing interfaces, even brine freezing. And all of these settings are capable of forming significant variety of prograde and retrograde ionic salts, minerals such as anhydrite, halite, bischofite, but they're not true evaporites. They are not solar-derived precipitates. In this module, I'm going to look at a variety of processes and drivers for the formation of these non-evaporitic ionic salts. We'll look at retrograde solubility in and near active mid-oceanic ridges where black smokers and white smokers are forming. We'll look at zones of deeply circulating marine brines in zones of serpentinite formation. We'll also have a look at zones of extremely high pressure and temperature where we see supercritical heating of a brine and the associated salting out of a variety of ionic salts. And then lastly, we'll have a look at what are relatively stable long-term mixing interfaces between rising magmatic waters and phreatic waters, both within the stagnant phreatic zone and in the active phreatic zone up near the water table. All of these processes and drivers are related to fracture-focused escape of mantle-derived fluids into reactive lithologies, forming interfaces where we see flushing by actively circulating phreatic, marine or non-marine waters mixing with these mantle-derived fluids. So let's move into this chapter, which is dealing with retrograde solubility in and near active mid-oceanic ridges. Let's remind ourselves, what is retrograde solubility? Well, we know that anhydrite is a retrograde mineral. The characteristics of a retrograde salt is that its heating lowers the solubility of that salt. So heating drives the precipitation of that salt. In that scenario, we form from seawater anhydrite. So anhydrite is a widespread hydrothermal mineral. It's also interesting that if we move into zones with temperatures below 320, 350 degrees, the typical fluid escape temperatures at mid-oceanic ridges, the anhydrite once again returns to a prograde nature whereby its solubility increases with heating. So there is a range of temperatures for anhydrite, up to around 300 degrees centigrade, where anhydrite acts in a retrograde fashion. But beyond that, anhydrite will go into solution once more, act as a prograde salt with increasing heat. That solubility of anhydrite is going to respond also to variations, not just in concentration, as we can see in this plot, but also to temperature. Retrograde solubility means heating a brine drives the precipitation of anhydrite. Anhydrite is a very widespread but ephemeral retrograde salt at oceanic spreading centers, and it's intimately related to the formation of volcanogenically hosted massive sulfide deposits. We emphasize this much more in our metal courses. We also saw in the hydrology of evaporites that anhydrite, because of its retrograde nature, is also forming nodular anhydrite in many of the classic modern sabkhas in the Arabian Gulf, in Abu Dhabi and in Saudi Arabia, where we have resurging, deeply circulated continental brines returning to the surface in the near coastal zone, and we form anhydrite as that brine's temperature rises as it moves towards the desert land surface. But in this situation that we're looking at in this chapter, we're looking at retrograde solubility on the seafloor where we have escaping brines. These are the classic smoker terrains. And I'm going to show you now a section of video from the Monterey Bay Aquarium Research Institute, which is illustrating the variety of black smokers and white smokers that we can see in different places around the world. Notice that we can have situations with very hot brines where particulates are precipitating, or situations like this where we have shimmering escape of hot fluids, and we see anhydrite often forming in that situation. So let's just sit back for a minute and enjoy this variety of rather impressive vents on the deep ocean seafloor, where a variety of black smokers, the metalliferous smokers, quite often with high levels of copper, are forming, versus the white smokers, where anhydrite is the dominant precipitate. Anhydrite's precipitating across both the black smoker and the white smoker terrain, but it dominates in the regions of the white smokers. Notice that life, chemosynthetic life, is quite common in these regions, with a variety of annelids and also shrimp, which are feeding on the bacterial mats, the chemosynthetic mats associated with these heat sources on the deep ocean floor, where we're a couple of thousand meters below sea level in many of these situations. So the driving process here is one of deeply circulating marine waters, where we have the downwelling interaction with hot basaltic host rocks. On the way down, the fluids lose all of their magnesium, oxygen, and sulfate. And then at the zone of their deepest penetration, approaching that heat source, those fluids heat, they become less dense, they rise, they become buoyant, and so they move back up toward the surface after passing through a zone where they can get quite warm, which is in excess of 400 degrees centigrade. When those fluids then return to the surface, they escape back into the oceanic realm, and so these superheated fluids are reacting with cold seawater. At temperatures in excess of 300 to 320 degrees, they precipitate their sulfide metals. Quite often they've picked up copper, zinc, iron, and sulfur in that circulation. And also, because they've lost their sulfate in the early stages of descent, once they return to the seafloor, interact with that sulfate in the seawater, and they precipitate masses of anhydrite. So we get these retrograde anhydrite precipitates, where we have heated, deeply circulated marine-derived waters returning to the surface. The anhydrite zones are the white smokers. The particulate black regions are the black smokers, the metalliferous smokers. This is just showing you for Tagmount, one of these zones that we'll look at, it's showing you the differences in the physical properties and the chemistry between the seawater, where we have temperatures of 3 degrees on the seafloor, and the black smoker, white smoker escapes. Remember, the black smokers are the metalliferous associations, the white smokers are the anhydrite-dominated associations. Anhydrite's also forming in the black smokers, but it's not necessarily dominant. And we can see the black smokers at Tagmount have temperatures in excess of 350 degrees, whereas white smokers are a little cooler. They tend to have temperatures of less than 300 degrees centigrade. Calcium values are enhanced over seawater in both the black smoker and the white smoker exits. They have little or no magnesium, little or no sulfate. The strontium levels are slightly elevated. The magnesium to calcium ratios have gone from 5 in seawater to 0 in the black smoker, white smoker vent outputs because of the loss of that magnesium in the descending arm of that circulation cell. And we also see they have somewhat distinct strontium isotope value. So let's look first of all at Tagmount, a classic black smoker active vent. Tagmount, by the way, comes from the transatlantic geotraverse. It's an acronym. It forms in an area surrounded by active deep water volcanics. In the Tagmount system, we are looking at 3,000 meters water depth, where we are looking at fractured seafloor basalts and volcanic debris. We'll also have a look at the Grimsey hydrothermal field offshore Iceland. The difference between Tagmount and Grimsey, and also the Guaymas Basin, is that in the latter two, Grimsey and the Guaymas Basin, we have sediment accumulating in with the smokers, the retrograde anhydrites. So the Grimsey hydrothermal field is hosted in Still fairly deep water, but it's hosted in volcanoclastics and glacial debris with a 100-meter thick basin fill. And the Guaymas Basin in offshore Mexico and Baja California is a little deeper. It's at 2,000 meters water depth. But what's distinctive here is that it's hosted in what are very organic-rich siliceous diatomites and methanogenic dolomites in a 500-meter thick basin fill. And there's a lot of thermally cracked hydrocarbons moving around in the Guaymas Basin. And as we discussed in the dolomite course, this is one of the reasons why we see these methanogenic dolomites dominating in the shallow subsurface. Okay, so let's now focus in on Tag Mound. Remember that this is a zone where we have little or no sedimentation taking place other than the volcanic debris associated with the formation of new oceanic basaltic crust. So this is the Tag hydrothermal zone. As you can see, it's in the mid-Atlantic. The Mura zone is the oldest, where the hydrothermal activity started about 140,000 years ago. It ceased, in terms of its last active measured episode, at about 600 years ago. The sulfides from the Double and the Shinkai mounds also are no longer active, and they yield activity ages of 50,000 and 2 to 23,000 years ago, respectively. The Rona, the Southern Mound, and the New Mounds 2 and 3, we don't have radiometric dates for them, but we know that they are probably, in being in the same province, related to the same timing as the Double and the Shinkai Mounds. Also, the fact that their slopes are showing evidence of anhydrite dissolution imply that they have a similar developmental stage in the Rona, the Southern, and the New Mounds 2 and 3. They're no longer active. We contrast that with the Tag Mound, which is in the southeastern portion of that seafloor map. Notice that we're at a depth here of around 3,650 meters at Tag Mound. The hydrothermal activity there has been dated as starting at around 50,000 years ago, and it's been episodic. So we have periods of activity from tens to hundreds of years interspersed by times of little or no activity. The active periods are characterized by the accumulation of both sulfides and anhydrites, along with various processes of replacement and refining of their metalliferous content. Throughout this 50,000 year period, we have inactive periods between 3,000 and 5,000 years long, characterized not by creation of new material on the seafloor, but by mass wasting, dissolution of anhydrite, and brecciation. Notice I said anhydrite. These mounds, the Tag Mound, which is an active mound, which started its activity around 80 years ago and is still actively forming, it has something like 50 to 60% anhydrite in the mound structure. Tag Mound is characterized by metalliferous black smokers at the crest of the mound with temperatures of up to 363 degrees and the escaping brines, and that summit is about 20 meters above the level of the upper platform position on Tag Mound. We also see something else here in the lower image that's quite interesting. Those white sausage-like features are shrimp. They're 4 to 5 centimeters long. They are grazing on the chemosynthetic bacterial carpet adjacent to these venting fluids. And we discussed the biology of these systems when we looked at life in saline environments in that free course on the Saltwork website. What makes Tag Mound quite interesting is that it is the largest single vent structure known on the seafloor surface today. It's about 200 meters across, so it's comparable in size to the Roman Colosseum. It's got an outer platform and then an inner platform, a venting platform. The white smokers tend to form in the periphery. The black smokers tend to form in the hottest crestal position of venting. So we have two superposed platforms, and they probably represent different phases of active growth. The more extensive, larger platform, by the way, this is showing you the positions of the cores that were collected on Tag Mound, Tag 1 through Tag 5 by Humphreys and others back in 95, and there's an excellent paper by Robert in 2009 describing the history, the geological history and its evolution of Tag Mound. So this is documented, not inferred, subsurface material. What's interesting is that that larger, lower platform, which is dominated by white smoker complexes, also shows widespread evidence of mass wasting. Because once that anhydrite forms by a retrograde process of cooling of brine, once those vents are no longer active, that anhydrite starts to dissolve. But where we do see active white smoker vents, the venting fluids on that lower, larger platform in Tag Mound have venting temperatures of between 260 and 300 degrees centigrade. Then there's a much narrower upper platform, and that's characterized by active metalliferous black smokers. These are quite cupiferous, and the temperatures there are relatively high. They range up to 365 degrees centigrade, and we have the vents containing upwards of 23% copper. So this is a volcanogenically hosted massive sulfide deposit in the process of formation. If we look at the mineralogy of the two smoker vents, the white smoker fluids and their vents are composed of anhydrite, along with some zinc sulfides, some low iron content zinc sulfides, with minor marcasite and amorphous silica in those white smoker vents. Whereas the hotter crestal black smoker fluids are precipitating a variety of anhydrite, chalcopyrite, with lesser anhydrite. If we look at the internal structure of the tag mound, we can see that there is, covering the crest of the upper position, a massive pyritic breccia. But below that, we have a range of anhydrite-rich material extending all the way down 50 meters into that succession. We have varying levels of anhydrite, with anhydrite dominating in the lower portions of the active venting region of the system. So geologically, we have this anhydritic upper portion where we see anhydrite forming an anhydritic cone as hot brine escapes onto the seafloor, with a crestal black smoker complex. And as we pass down, further down, we get into a silicified pyritic stockwork, and further down into a chloratized and hematized basaltic structure. So this is classic VHMS type zonation in Tag Mound. It's been estimated by Hannington in a paper back in 1998 that Tag Mound and its underlying network of channels contains something like 3.9 million tonnes of massive sulfide. So what the black smokers and the white smokers on Tag Mound clearly show is that there is a sequence of growth stages in the development of the vents in Tag Mound. We have the earlier, and also in the cooler portions, the white smoker stage, where we have anhydrite dropping out of solution, where we have mixing between seawater and the hydrothermal fluids coming out of the vent. We have mixing of fluids in excess of 150 to 250 degrees, mixing with 2 to 3 degrees seawater, driving the retrograde precipitation of anhydrite. In the hotter black smoker stage, where we have active metalliferous sulfide chimneys forming, some call this a more mature stage. This is what's happening near the crest of the Tag Mound, where we have fluids in excess of 300 degrees centigrade. We see a range of sulfide minerals forming from these high temperature fluids, and we also see particulates forming in the seawater above the venting chimneys, whereas we tend to see shimmering waters above the sulfate chimneys. So in the mature stage, we see, once again, mixing between hydrothermal fluids and seawater, but at higher temperatures, and we see a zonation into the various mineral stage assemblages. And we discuss these in detail in the metalliferous set of modules. We see intensive, somewhat stable thermal geochemical gradients within the chimneys. We also see there's a high abundance of biomass in both of these stages, where there are bacterial mats living on the exterior of these chimney structures. We see riftia, the annelids, and a whole range of shrimp feeding on these systems. So we see quite a diverse microbial zonation with a variety of megafauna living on that chemosynthetic bacterial association. Once the chimneys become inactive, we see no venting, and so we see a weathered sulfide chimney and the anhydrite starts to dissolve. So a white smoker is a vent composed mostly of anhydrite with some zinc sulfides, and we have a high pH hydrothermal fluid coming out of these chimneys. In the cooler stages is the anhydrite stage, and in the warmer stages are the metalliferous black smoker stages. So we can think of it as an association in the white smokers, and also perhaps the earlier stages of chimney formation dominated by anhydrite, and then a second stage dominated by the precipitation of sulfide minerals, but still with some anhydrite forming on the outer portions of the growing black smoker vents. So let's move now to the Grimsey hydrothermal field north of Iceland, where we have sediment-hosted white smokers forming from somewhat cooler fluids than we saw in Tag Mound. They are forming within a surrounding matrix of volcanoclastic and glacial sediments. Grimsey hydrothermal field is located at the southern end of the mid-oceanic ridge, extending well up into the high Arctic. And we can see that along that oceanic ridge, we have a range of active hydrothermal fields. Grimsey is one of them, along with extinct fields such as squid forest, and also a series of shimmering waters or hydrothermal plumes, indicated in yellow, escaping along that ridge structure. In Grimsey itself, we are looking at what is the mid-oceanic seafloor ridge region, where we're seeing significant levels of retrograde anhydrite forming hosted in the sediments of the Grimsey graben in the region of the Yawn fracture field. So at Grimsey, there's an active fracture zone, the Yawn fracture zone. It's located at a jump of some 75 kilometres between the main oceanic ridge as it hits Iceland and where it exits to the north. We have that Yawn fracture zone, and associated with that, we have a pull-apart basin with sediment accumulating. Now, in the Grimsey hydrothermal field, we see white smokers, active and inactive white chimneys up to 3 metres high, sitting atop hydrothermal anhydrite mounds, which are some 20 metres in diameter. This succession sits within a zone where we are looking at sediment-hosted accumulations, not volcanic breccia-host accumulations, but accumulations in sediments, clay-dominated, relatively deep water. Water column's about 400 metres, and the actual hydrothermal area is about 300 by 1,000 metres across. The sediment itself is accumulating from what is the weathering products of ice-fed rivers draining Iceland, along with associated volcaniclastics and volcanics coming from a variety of volcanic eruptions. So filling that graben, we have a variety of glaciogenic and volcaniclastic sediments. And the hydrothermal activity then is taking place within that sediment column, unlike where we have open oceanic ridges with little or no sediment accumulation. In the Grimsey field, it's hosted in altered sediments. These chimneys are up to 3 metres high, atop these anhydrite mounds, and we have cooler waters than we had escaping in the crest of Tag Mound. The waters exiting here are at temperatures of up to 250 degrees. So we're below the 360 degrees that was forming the black smokers in Tag Mound. If we look at the fluid inclusions in the anhydrite, we see that the anhydrite fluid inclusion temperatures show the same homogenization temperatures as the fluids that are escaping from the vents, in that range 200 to 260 degrees centigrade. If we look at the mineralogy of the vent material, we can see it's dominated by anhydrite. Some of it's reconverting back to gypsum before it's completely dissolved. And we also see orthogenic clays like stevensite forming in some of the vent material. If we look at the sulfur isotope data, it's marine. They have typical seawater values of around 22 parts per mil, which indicates a seawater source. This is the same range that we see in evaporites. We see the same sulfur isotope signatures here as we see in marine-derived solar evaporites. If we look at the proportion of the samples in Grimsey field, the anhydrite contains something like 22 weight% calcium, 1500 ppm strontium, so it's somewhat higher than the Tag Mound, and around 3.47 weight% magnesium. These numbers are more influenced by the sediment which the vent fluid is interacting on its way up to the surface. And if we look at the strontium isotopic ratios, they average out at around 0.70662, once again implying that anhydrite is precipitating from a hydrothermal seawater mixture. The deep-seated hydrothermal fluid has a value of something like 0.703 to 0.704, which as it mixes with seawater that's circulating in that system, gives it that mixed value of around 0.706, indicating a mixing between 40% upwelling hydrothermal water with 60% heated seawater having a value of 0.7092. So the anhydrite isotopic ratios that we see in that circulation cell are telling us the same thing. As we saw in Tag Mound, we are seeing a mixing between deeply circulated, sulfate-depleted water and rising hydrothermal waters coming off that magmatic source. So here's some of the anhydrite that dominates in these mounds at Grimsey, And it's forming in this zone of mixing between the upwelling, deeply seated hydrothermal fluids and the shallower circulating seawater, which the strontium isotopes are telling us is a ratio of something like 40 to 60. Before and during the mixing, we have on the descending arm that seawater being heated to 200 to 250 degrees, and then as it escapes, it forms retrograde anhydrite in those zones of local heating of normal marine waters. This is the same process that's happening in the Kuroko deposits in the Hokkaido Basin in offshore Japan, the classic area for VHMS deposits forming in sediment-hosted associations. If we look at the various forms of anhydrite, there's a range of structures. We can see it has what's called a beehive texture, an open vesicular texture, up into massive textures. A lot of the anhydrite, because it's growing from point nucleation, is radially fibrous. But we can also see some rectangular anhydrite, coarser rectangular anhydrite forming. And we also are forming a orthogenic clay, a talc-like material, which is coating some of the euhedral platy anhydrite. That talc-like material, it's kerolite. This is the primary phyllosilicate precipitate in the vent at temperatures of around 300 degrees before it exits at a much cooler temperature. And so the collapse of the chimney and the subsequent dissolution of these mounds is forming the somewhat permeable aquifers that underlie the main Grimsey Mound. So here we have the same process we see in solar evaporite deposits, where we see dissolution of evaporites creating aquifers that facilitate subsurface circulation. If we look a little bit broader at what happens in these active circulation cells, what's happening to the volcaniclastics, this hydrothermal circulation is converting the volcaniclastic material to smectite, the expansive clay, the montanurite clay, smectite. This is happening at somewhat cooler temperatures, ranging up to 95 to 116 degrees centigrade. We form phyllosilicates as primary precipitates, kerolite or talc precipitates, in and around the vents that can be reworked into the surrounding sediment. We also have the hydrothermal conversion of the volcaniclastic, the labile volcaniclastics, into smectitic clays. Here we don't just form retrograde anhydrite. The retrograde anhydrite is forming an aquifer system which enhances alteration by circulating hot hydrothermal fluids through a broader context of sediment. We also have a more regional conversion of volcaniclastic material to smectite. In the third and final example, I want to look at an example where there's a lot more organic material. So we're going to go to the Guaymas Basin in the Gulf of California. It's offshore Mexico, Baja California. It's an analogue to the Beshi-style VHMS deposits. Guaymas Basin is east of the Baja Peninsula, offshore Mexico. It's forming a basin where there are two main structures. There is a northern trough and a southern trough. And we're going to focus in on the southern trough, indicated by that position of the star, which is the position of one of the first wells to document the hydrothermal anhydrite here and the alteration of the associated organoretic sediments. That was DSDP 477A. So across a strike length of something like 120 kilometres, there are a variety of metalliferous hydrothermal vents that are hosted in what are silicious biogenic diatomite silicious oozes along with turbidites. And that sediment column, the hosting sediment, is about 500 metres thick. And that sediment is covering a series of spreading ridges and transform faults, indicated by the troughs, with a variety of stacked igneous sills penetrating and heating the sediment column. We're looking here not purely at venting. Here we're looking at a circulatory system where we see dolerite sills penetrating into that 500-metre sediment column and heating that sediment. And so some of the shallow intrusions are some 400 metres below the seafloor in water columns that are in excess of 1,800 metres. So this is deep water sedimentation hosted in diatomaceous oozes. And in there we find that there is the isocubinite, the cupiferous iron sulfide salt, cubinite, in many of these vents. So this is another region where we're seeing hydrothermal metalliferous accumulations, in this case hosted in deep water sediment, so it's a Beshi-style analogue. If we look at the isocubinite that's forming in here, it's usually intimately intergrown with iron and zinc-rich chalcopyrite, and it appears as lamellae. These are exsolution textures of chalcopyrite exsolving from isocubinite. So here we have the early stages of a VHMS copper-rich deposit. This map is showing you the distribution of the various vents and the documented underlying doleritic sills indicated in grey. The red is showing you the area of the next image, showing you the position of various hydrothermal rich associations on the floor of the Guaymas Basin in water depths in excess of 1800-1900 metres. So the temperatures in some of these vents are more elevated, much warmer than in the Grimsey hydrothermal field. We get exit temperatures as high as 315 degrees in some vents. And so we don't just see sulfates and talcs, the hydrothermal phyllosilicates. We also see pyrrhotite, sphalerite, wurtzite, marcasite, and chalcopyrite. So we're back in the range where we've got venting black smokers precipitating metalliferous sulfides. What's interesting here is that this region is also known for its very organic-rich sediments, where we have not the usual burial-related generation, catagenic generation of hydrocarbons. Rather, we're seeing it thermally cracked by these hot emplacement sills, cracking quite immature organic-rich sediments. So we heat up these organic-rich diatomaceous oozes and we form hydrocarbons. And also because of that organic-rich methane generation, it's also the type area, as we discussed in the dolomite course, for methanogenic dolomites, which are forming a few tens of meters below the surface by the activity of methanogenic archaea. This is what the various vents look like, and here we can see the anhydrite smokers. Notice also here that there's this very widespread white snow-like accumulation. These are bacterial mats, and there are also hydrocarbons escaping from these vents. Here's a layered vent. It's also got the annelids, the riftworms, riftia, this chemosynthetic community, typical of hydrothermal vents, very rich hydrothermal community. But what's interesting here is that we also see globules of hydrocarbons, the browns here, escaping from the vent, and this is right next to a set of riftia juveniles. And so we get these weird and wonderful shapes where we've got these cooling outflowing waters, we've got worm tubes, we've got a whole variety of mats forming, bacterial mats. And these structures can be as much as 5 meters above the surrounding mound, and that mound itself is rising another 5 to 25 meters above the seafloor. The chimneys, the vent chimneys in the Guaymas Basin, are dominated by mixtures of anhydrite and pyrrhotite with lesser amounts of the other metal sulfides, the zincs and the copper sulfides. The Guaymas mounds grow upwards, sideways and downwards depending on how the minerals precipitate and clog the vents. So we get a whole range of shapes ranging from simple conical shapes to multi-tiered pagoda-like spires with a whole range of subhorizontal eaves with quite often brine mirrors sitting under those eaves. Once venting ceases, the chimneys become unstable, they collapse. If there's still solutions present, when they collapse, the vent base breaks and chimney growth begins once again, and it encompasses those broken fragments into the chimney structures. In contrast to the non-sedimented spreading centres at mid-oceanic ridges that are favoured by magma emplacement along axial valleys, these sediments in the Guaymas Basin are acting, because they're so organic rich, as a thermal blanket. So we get much broader zones of magmatism here, interacting with the sediment, forming axial parallel faults that are extending out into the sediments in off-axis flanking positions. So these sills alter the organic hydrocarbon content. They thermally crack the hydrocarbons, and so we get buried organic carbon acting as a reductant for thermochemical sulfate reduction and the bacterial sulfate reduction that is fixing the metal sulfides. So if we look at the delta 34S values for the sulfate minerals in the mounds, there's a range. We're not just around the 22, 23 values for seawater. We get a range from 16.1 to 23, in part reflecting the influence of bacteriogenic reactions. And also we see for that barite precipitation a range of values from 23.1 to 29. Those values are laterally consistent. So this is the map showing you the position of the ODP well 477 and some adjacent mound structures. The inset is showing you hydrocarbon globules escaping from the seafloor in that region. The sulfate values, they're being plotted against distance from that 477 well. Those sulfate values are quite consistent. There's a little bit of variation related to sulfate reduction of that hydrocarbon-rich association. Still, they look pretty marine in terms of the range of values. It indicates retrograde precipitation. of a relatively unfractionated seawater sulfate source for both the anhydrite and the barite. But when we look at some of the sulfate values, they got these more negative values because of sulfate reduction or sulfate oxidation related to microbial processes. If we look at the sulfides once again are internally consistent with distance from DSDP 477, but they are much more negative, and they're probably indicating the association with bacterial or thermochemical sulfate reduction. The other thing to remember here is that because this anhydrite is dissolving under these seafloor conditions, it's usually gone when we look at inactive vents. And this is a characteristic feature of all of these vent deposits. The anhydrite doesn't hang around, but it goes. Through its going, it can create aquifers which facilitate broader hydrothermal circulation. In the Guaymas Basin, we do see some remnant gypsum. This is not evaporitic gypsum. This is remnant gypsum from the alteration of anhydrite to gypsum, which is a little bit more stable. And so some of the cores that are taken in areas where the venting is no longer active, we see gypsum, not anhydrite, preserved. But this is a zone where we have oily anhydrite. It's a zone where we have abundant hydrocarbons. So if we look at the chalcopyrite or the precursor isocubinite structure, it consists in the vents in what is a strongly covalent configuration with effective ionic states ranging between CuFeS and CuFeS2. So we need an oxidizing agent to convert the ferrous iron or the cuprous copper that's being supplied by the hydrothermal fluid to fix it as either the ferric or the cupric state in the isocubinite, the metal sulfide that's forming in these vents. Now, since isocubinite precipitation requires high temperatures, then in the most restricted mixing conditions, which is required for its formation, it's very likely that we haven't got much dissolved oxygen in the seawater. Oxygen is an unlikely oxidizing agent. The most likely oxidizing agent is sulfate derived from the anhydrite. So once again, here is a salt, in this case not an evaporite salt, but the calcium sulfate from the anhydrite, acting as a source for sulfate for the fixation of metals. And we deal with that a lot more detail in the copper course, which is available for enrolment on the Saltworks website. To finish off this discussion of retrograde anhydrite in mid-oceanic ridges, let's think a little bit about what texturally the presence and then the dissolution of that anhydrite means. All VHMS deposits were once quite salty. The anhydrite in active vents like Tag Mound and Grimsey makes up the dominant mineralogy in the zone of venting. But once that hydrothermal circulation stops or slows, then as the temperature falls below 150 degrees centigrade, the anhydrite starts to dissolve. Remember, it's a retrograde salt, so if we lower the temperature, it becomes more soluble. During inactive periods on the vents, in any of these regions, dissolution leads to the collapse. So we get the equivalent to an evaporite dissolution breccia forming, but it's a ionic salt dissolution breccia forming by the dissolution of anhydrite in these structures. And so we form many metalliferous breccia structures, as we can see in these sulfide breccias from the Semenov 3 hydrothermal field in the mid-Atlantic, where the structures mimic the types of textures we see in evaporite dissolution breccias. There's certainly what was once a hosting calcium sulfate system, an ionic salt there, that's been dissolved away as temperatures cooled, and we now form these clast-to-clast breccia associations made up by, in this case, the metalliferous clasts. And of course, there's going to be ongoing disruption by faulting in these active tectonic areas as well. Most of our metalliferous structures in these VHMS deposits are brecciated by a combination of tectonics and anhydrite dissolution. Through its dissolution, through its going away, former zones of anhydrite, the hydrothermal anhydrite, give us intervals of enhanced porosity and cavities in the mound. That initiates further fracturing and aquifer access. They become permeable pathways during later renewed fluid circulation events. And so this coming and going of hydrothermal anhydrite is creating precipitation spaces within the mound hydrology, which has textural similarities to classic evaporite dissolution breccias in mineralized sedimentary systems, not hydrothermal systems.